Hello, this is the section 4.2 lesson. Section 4.1 we talked about what is statistics, why are we doing it, some different types of data and how to collect them. Section 4.2 we're going to start talking about what do we do with that data once we have collected it. Now, quick note for this lesson, you're going to need your calculator because here in a bit we're going to talk about how we can use the calculator to perform some of the calculations in this section. So let's briefly review this scenario that we introduced in section 4.1 where a grocery store manager is studying ways to improve customer satisfaction. And specifically he's interested in the amount of time customers spend waiting in line. And so he might ask these three questions about that wait time. So we drew this picture here to illustrate some of the ideas involved. So we've got our two worlds here, the real world, the math world. Of course, we live in the real world. We ask questions in the real world. We want answers in the real world. But we use ideas from the math world in order to answer those questions. So here's our three questions. What's the expected wait time? What's the probability a wait time is greater than 10? What's the variation? Over here in the math world, we define this random variable x to be the wait time of a customer. And then our questions in terms of x are, what's the expected value of x? What's the probability that x is greater than 10? What's the variance of x? So he said that if we know the distribution and the appropriate parameters of that random variable, well, then we can very easily calculate these three quantities and we have the answers to our questions. So in order to know that distribution and the appropriate parameters of x, we have to go back here to the real world and collect some wait times of actual customers. So we need to observe some real customers, record the amount of time that each one of them waits in line. Those observations are what we call observed values of x. We're also called data. And so now we're going to talk in this section, talk about what do we do with that data to help us answer this question, what's the appropriate distribution and parameters of x? So here in this example, let's suppose that we've gone out and we observed 30 customers standing in line, and each customer we recorded the amount of time they spent standing in line. And so we've got our data here arranged from smallest to largest. We had 3 customers that waited 0 minutes, 2 customers waited 0.2 minutes, another customer waited 0.3 minutes, so on and so forth. One customer waited as much as 7.3 minutes. So these data are arranged in increasing order, not necessarily in the order that we actually observed them. So the first thing that we might do is draw a graph of these data. Now there's lots of different types of graphs that we could draw, and in the book we talk about some of the more important types. Probably the most important type of graph, though, is what we call a histogram. And in order to set up a histogram, first we construct this relative frequency distribution that we've talked about before. So the idea here in a relative frequency distribution is we're going to take our range of data values, which go from 0 up to 7.3, and we're going to break that interval up into several subintervals, or also called bins or classes. And so here I've chosen to use 8 different subintervals, each one of with 1. And then we calculate, or we count the number of data values in each one of those intervals. So we have 10 data values in this interval, 7 data values in that interval, and so on and so forth. Next, we calculate a relative frequency by dividing each one of these frequencies by the total number of data values, which is 30 in this case. And so there's our relative frequencies. And another thing we can calculate is our cumulative relative frequencies, where we just take a running total of our relative frequencies. So this number here is just this first relative frequency plus the second. This number here is this cumulative relative frequency plus this relative frequency, and so on and so forth. So that's our relative frequency distribution. Next, we draw a picture of that relative frequency distribution in the form of this histogram. So here our horizontal axis is our values of our random variable. Each interval we've got one column here, and the height of that column is our relative frequency. And so there's our histogram. We've drawn this before, so I'm not going to go into much details as to how to do that. Over here is our cumulative relative frequency histogram, where instead of plotting relative frequencies, we plot cumulative relative frequencies. But the important graph here is this relative frequency histogram. One reason that this is very important is because the shape of our relative frequency histogram is an approximation of the graph of the PDF or the PMF of the underlying random variable. So here our underlying random variable is this random variable x representing the wait time. We want to know what type of distribution this has. We can get an idea of what type of distribution it has by looking at the shape of this histogram. Notice that the histogram starts tall and then it quickly decreases to very short. So we think, well, wait a minute, what type of distribution has that type of graph? And we say to ourselves, well, wait a minute, it looks kind of like an exponential distribution, right? If we graph the exponential PDF, it looks kind of like this. It starts high and it quickly decreases to low. And so right there, looking at the shape of that relative frequency histogram gives an indication that our underlying random variable has an exponential distribution. Now, next thing we can do is calculate what we generically call summary statistics. And these are all probably values that you're somewhat familiar with. So this says let x1, x2, up through xn be a set of quantitative data collected from a sample of the population. So quantitative data means that our data are numbers representing counts or measurements. And we've got n data values. So n here is our sample size, the number of data values that we've collected. The first summary statistic we can calculate is called the mean of the data. Now this is not the same as the mean of a random variable. There's a relationship, but there's a fundamental difference here. The mean of a data is where we have a sample data and we calculate this thing called the mean. The mean of a random variable is a little bit different idea. There's a relationship that we'll talk about here in a bit, but they are not the same ideas. Okay? So to calculate the mean of the set of data is we add up all our data values and divide by the total number of data values. That's all there is to it. Next, we have the variance of the data. The variance of the data is denoted lowercase s squared. And this formula says that we take each data value, we subtract the mean of the data, we square it, we add them up, and then we divide by n minus 1. And that number is called the variance of the data. Now, take a quick step back. The mean of the data is denoted by this lowercase x bar. The next summary statistic called the standard deviation of the data. The standard deviation is just the square root of the variance. So we denote the standard deviation s, and it's equal to the square root of the variance s squared. The last summary statistic here is the range of the data, where we take the maximum value minus the minimum value. Now, these summary statistics are also called sample statistics. Remember, back in section 401, we defined sample statistics as numbers that were calculated using information from a sample. And that's exactly what we're doing here in all these summary statistics. We're taking data from a sample, we're calculating a number. Those numbers are generically called sample statistics, or also summary statistics. Now, these values can all be calculated on the calculator, but let's just show how we could do them by hand if we really wanted to. So first of all, the sample mean, we simply add up all of our data values, divide by the number of data values, 30, and we get our mean, which is 2 in this case. To do the sample standard deviation, we take each data value. Here we'll take the first data value, subtract the mean of 2, we square it. Then we take the next data value, subtract the mean, square it. Do the same for each one of the data values. Here's our last data value, 7.3, subtract the mean of 2, square it. We add them up, and then we divide by n minus 1, which would be 29 in this case, and that comes out to be 2.946. Okay. The sample standard deviation S is just the square root of the variance. So square root of 2.9 is about 1.73, 1.72. And then the range, you take the maximum value minus the minimum value, you get 7.3. So that's all there is to calculating these summary statistics. Maybe a little bit tedious, but not terribly complicated. One quick note here about the units. Notice that the units on the mean, the standard deviation, and the range are all the same units as the original data, which was minutes, and the units on the variance are the units squared. Okay. Now, one very, very important point to remember about these summary statistics is this. So remember we said that data are observed values of a random variable x. In this case, our random variable is the wait time. Our data are observed wait times. Now with the random variable, we calculated things like the expected value. We also called the mean. We denoted it mu. We also calculated things like the variance of the random variable. We denoted that sigma squared. We also calculated the standard deviation of the random variable. We denoted that sigma. Now, a sample mean x bar is approximately equal to the expected value of the random variable. So a sample mean is an estimate or an approximation of the mean of our random variable. Likewise, a sample standard deviation s squared is an approximation of the variance of our random variable. A sample standard deviation is an approximation of the standard deviation of our random variable. So, in other words, in generic terms, sample statistics are estimates of the parameters of the random variables. Remember, these numbers mu and sigma squared are what we called the parameters of the random variable. These numbers over here are sample statistics. What we're saying here is that each sample statistic is an approximation of the corresponding parameter of the random variable. Now these estimates are also what we call point estimates, meaning they're one number estimates of those parameters. Here in a few sections we'll talk about some other types of estimates that we can get, but right now these are just one number estimates, so they're called point estimates. And our parameters of the random variable are generically called population parameters. It's another term that we defined in section 4.1. Here we're just making a connection between that definition in section 4.1 and the underlying random variable. Now, another type of summary statistic that we can calculate are called percentiles. And so let's define the 80th percentile of a set of quantitative data is a number that's greater than about 80% of the other data values. And an 80th percentile is denoted pi sub 0.8. Now, there's nothing magical about the number 80. We could change that to any number between 1 and 99. So we could talk about the 1st percentile, the 25th percentile, the 99th percentile, a lot of different percentiles that we could calculate. But they all have the same basic meaning. 80th percentile is a number that's bigger than about 80% of our other data values. A 90th percentile would be a number that's bigger than 90% of other data values. 10th percentile is a number that's bigger than about 10% of our other data values. Okay. Now, some special percentiles that we talk about are the 25th, the 50th, and the 75th percentiles, and those are also called the first, second, and third quartiles. And those are denoted with some different symbols. The first quartile is denoted P1. It's also called pi sub 0.25. Second quartile is P sub 2. It's also denoted pi sub 0.5. And then the third quartile is denoted P sub 0.75, because these are the 25th, the 50th, and the 75th percentiles, as we just defined them in the last slide. Now, the 50th percentile is also called the median of the data, and it's also denoted M. So the median is denoted M. It's also denoted P2. It's also denoted pi sub 0.5. Lots of different symbols for the same idea, the median. The median, the 50th percentile, is a number that's bigger than about 50% of all of our data values. Now, let's quickly talk about a simple algorithm for calculating percentiles. Not every statistics book and piece of statistical software calculates percentiles in the exact same way. Here's a relatively simple algorithm. So we want to calculate pi sub p. So if we want to calculate the 80th percentile, p is 0.8. If we want to do the 50th percentile, p is 0.5, so on and so forth. First thing we do is arrange the data in increasing order. x1 is our smallest, x2 is our next smallest, xn is our largest. Next we calculate L, which is equal to n times p. Now if L is not an integer, then we round it up to the next larger integer, and our percentile is equal to that particular data value, x sub L. If L is an integer, then we take that data value plus the next one and take the average of those two. So let's illustrate this this with an example. Here's our data. Notice that they're arranged in increasing order. So here's x1, x2, x3, x4, x5, x6. This would be x30. And let's calculate the first quartile, denoted p1, or also pi sub 0.25. So the first thing we calculate is L, which is equal to n times p. Comes out to be 7.5. Now that's not an integer, so we round it up to the next integer, which would be 8. And so our first quartile would be x sub 8, so our 8th data value. So 1, 2, 3, 4, 5, 6, 7, 8. That right there is our first quartile, 0.5. Let's calculate our median, denoted m, also p2, also pi sub 0.5. So we're going to follow the same basic steps. We're going to calculate L, which is n times p. Now notice that comes out to be a whole number, 15. And so our median is going to be the average of the 15th and the 16th data value. Okay, so let's find the 15th and the 16th. So there's 3, 6, 9, 12, 15. This right here is our 15th data value, and this is our 16th data value. So we're going to add those up, divide by 2, and there's our median, 1.8. Now let's do the same thing for the third quartile, denoted p sub 3, which is pi sub 0.75. And so we calculate n times p, 22.5. That's not a whole number, so we round it up to 23. And so our third quartile is the 23rd data value. So there's 3, 6, 9, 12, 15, 18, 21, 24. So this would be the 23rd data value, 2.9. So there we go. There's our first, second, and third quartiles. So this data value here is 0.5. That's our 25th percentile. That means that 0.5 is bigger than about 25% of our other data values. This is our median, which is our 50th percentile. That means that 1.8 is bigger than about 50% of our data values. This is our third quartile, or the 75th percentile. It means 2.9 is bigger than about 75% of our other data values. Now a couple of more quick definitions, and then we'll get to how to do these calculations on the calculator. First definition is our 5-number summary. 5-number summary of a set of data consists of the minimum value, the first, second, and third quartiles, and then the maximum value. So here's our set of data, and so the 5-number summary is the minimum value, which is 0, our first, second, and third quartiles, which we just calculated, and then the maximum value is 7.3. Next definition, the box plot is a graphical description of our 5-number summary. And so here's our 5-number summary for this set of data. To draw a box plot, we have a horizontal axis here, which represents the minutes, and then we put a short little tick mark here at our minimum value. We put a longer line at our first quartile, another line at our second quartile, Another line at a third quartile, and then a short little tick mark at our maximum value. And then we just finish it off so it looks like this. Okay. So what does a box plot allow us to do? Well, it kind of shows us, it gives us an idea of the distribution of our data. Now between our minimum value and our first quartile, there's 25% of our data values. So 25% of our data values are distributed over this relatively narrow interval. Between the first quartile and the second quartile, there's another 25%. So the second 25% are distributed over a little wider interval. Between the second quartile and the third quartile, there's another 25%. Those are distributed over a little bit narrower interval than that. But now look at this last interval. From the third quartile up to the maximum, there's our last 25% of the data values. Notice those are distributed over a pretty wide range of values. So we got kind of a lot of data values bunched up here, but then another bunch that's spread out over a larger value. So there's a box plot. That's how to calculate it. That's how to draw it. Okay. One last definition: the mode of the data is the data value that occurs most frequently. And so if we look at our data, we see that the number 0 occurs 3 times. Every other data value occurs 2 times or less, so the mode is equal to 0. Alright, enough calculating by hand. Let's let the calculator do some of the work. So this is really our first time that we've let the calculator do the work. So the first thing we need to do is set it up so that everything will work properly. So we need to set up our data editor. If you go to the Stat menu, which is right next to the left arrow key, press Stat, you'll get a window that looks kind of like this. You see there's 3 submenus there. If you choose the first submenu, Edit, and then either scroll down to number 5 or just hit the number 5, you'll see the Setup Editor pasted back at your blank home screen. You hit Enter, it'll say Done, and that means everything's set up. Okay. Next thing we need to do is enter our data. So if you again go to the Stat menu and then choose that first sub-menu, Edit, and then the first option, Edit, you're going to get a screen that looks kind of like this. You should see L1, L2, L3. These are different lists where we can enter data. If you scroll to the right, you'll see some other lists. And so we're going to enter our data here in our first list. So you just enter the first number, hit Enter, the second number, hit Enter, so on and so forth. It's pretty quick and easy to do. Okay. Next thing we're going to do is calculate our summary statistics. So if you go to the Stat menu and then scroll to this second submenu called Calc, and then choose this first option, 1var stats, by either scrolling down to it or pressing the 1 button. And then when you do that, at your blank home screen, you'll see this 1var stats pasted there. And then we need to enter the name of the list containing our data. And so if you hit the second button and then the 1 key, it will enter an L1 there. Now if your data was in L2, then you'd hit second 2. If your data were in L3, you'd hit second 3, and so on and so forth. So then you hit Enter again, and you should get your results that look like this. Now, like every other good piece of statistical software, the calculator gives us a lot more results than what's really necessary. So let's look at the results, figure out what's important and what's not. So first of all, the first line says 1var stats. That just means that it calculated the one variable summary statistics. The first number is x bar, which equals 2, so there's our sample mean. Next is capital sigma x. That's the sum of all of our data values. Now that's not important for our purposes, but it could be in some situations. Next, sigma x squared, that's the sum of the squares. Again, not important. Sx, that's our sample standard deviation, 1.716. It's identical to what we calculated by hand. So that result's important. The next one, sigma x, that would be our population standard deviation if we had values from every single member of the population. We don't have that, so it's not meaningful. Okay? The next, n equal 30, that's our sample size. Now you see this little down arrow that indicates that there's more results. So if you scroll down, you see these 5 results. There's the minimum data value. There's Q1, which is the first quartile. Now, the book we denote it P1, whereas the calculator calls it Q1. Doesn't matter. It's the same value. Here's our median. This the 50th percentile, 1.8. Here's our third quartile, and here's our maximum value. So this right here is our 5-number summary. Okay. Now, next, let's talk about how we can do some of these graphs on the calculator. So first graph, let's talk about doing the histogram. So if you hit second and then y equals to go to the stat plot, you'll see a window that maybe looks something kind of like this, where there's 3 different plots that we can work with. Now we're going to press 1 to select the first plot, and then you should get a window that looks maybe something similar to this. So you see plot 1 is highlighted. That means it's turned on. You see the on is highlighted. Again, that means it's turned on. Now there's 6 different types of statistical graphs the calculator will do. We're going to choose this third type, which is the histogram. And next we need to enter the list containing the data, which is L1. It should be the default value. If it's not, then you can hit second 1. And then, this is the step that everyone forgets to do. We have to do zoom option 9 for zoom stat. This is going to set our window to the right size so that we can see our histogram. And if you do this, you should get a graph that looks like this. Now you also need to make sure that all your other graphs are shut off. So make sure there's nothing else at the y equals menu. But you should get something that looks like this. Now, one thing that you can't control in the calculator is how many bins that it selects, or the width of the bins, or anything like that. Well, luckily we can easily figure out what bins the calculator used. If you press the trace button, you should get a little cursor there on the first column, and you see that this first subinterval goes from a min of 0 to a max of 1.22, and there are 12 data values in that first interval. Now that's a little bit different interval than what we used. The calculator has its own algorithm for determining how many intervals to use and how wide they should be. I don't know exactly how it works, but it usually works pretty well. So now if you scroll to the right, you'll go to the next bin, and you can see that bin goes from 1.22 up to 2.43, and there are 7 data values in that bin, and so on and so forth. So the histogram is calculated a little bit differently than what we did by hand, but notice that it still has the same shape. It starts high and very quickly decreases. So that's an indication that our underlying random variable has an exponential distribution. Okay. Now lastly, let's talk about doing a box plot. This can done if you go back to the stat plot menu. So go back second, y equals, choose plot 1. Now make sure it's turned on. For the type here, we're going to select this 5th type. There are 2 different types of histograms it'll do. We're going to choose the second type, so scroll over that, make sure it's highlighted, press enter. For the X list, again, choose list L1. Press zoom, and then 9 for zoom stat. Again, don't forget that zoom stat, and your window should look something like this. Now this box plot looks nearly identical to what we had drawn earlier. If you hit trace, you can see the 5 numbers in our 5-number summary right there. If you hit trace, you'll see the median is equal to 1.8. If you scroll to the left, you'll see the first quartile and the minimum, and so on and so forth. So feel free to use your calculator to calculate these summary statistics, these 5-number summaries, and do these different types of statistical plots.